let's construct few more boundary conditions. Okay, so let's say these boundary conditions is about the pulsatile flow or pulsatile blood flow, actual blood flow. Okay, so this is, let's say, from the MRI data we add up some blood flow signal in some of the our arteries, okay, that will supply the blood to either brain or any other organ of our body. Okay, so this is one class of the signal we got, okay, from the MRI data, and then we do the post process this signal and we try to construct the proper boundary condition with the taking into account the different mode. Okay, and we adapt this u equal to nothing but me into all these terms, and we able to generate entirely this particular let's say waveform. Okay, so that is the or wave for one particular heartbeat. Okay, and the period of it is let's say 0.928. Okay, and if we look at its mean amplitude, it has some mean amplitude. Okay, so over this it try to fluctuate, that is the idea. Okay, so let's say we have to go with this particular boundary conditions and we want to develop this class of boundary conditions. Okay, so what is needed, we require some mean flow, okay, and we require some period, okay, and then we have to construct some constant like a pi, and we have to take a time. Okay, and if we know this all the quantities, it's very easy to generate this class of boundary conditions. Okay, it's not going to be much difficult. Okay, so let's proceed then. Okay, so development of this BC. So if we want to develop this BC, it is again the in the time domain. So what I am going to do, I try to develop this BC based on our previously developed code. So let's say in the backup we have a time varying parabolic class of BC. Okay, so let's copy this. Okay, and based on that we try to construct this entire new BC. Okay, so let's say in the code area I already have this. Okay, so but I want to show you very quickly how one can generate. So few things we try to add up from here. So let's say give a some new name, inlet pulsatile BC. Okay, so that is what we want. So inlet pulsatile is the name I am adapting from here. So let's say rename as a inlet pulsatile BC. Inlet, I want I as a small letter, pulsatile BC. Okay, so let's add up this name. Okay, immediately inlet pulsatile BC, and let's give a name as a my, that is better, so we are consistent with our naming. So in my inlet pulsatile BC C. Okay, so immediately first to clean the our folder, so go to that folder, let's say wclean clean.all. so we are ready with the our folder. Now rename it, so it is going to be the vector field, so no worry, fv patch vector field only, control V, BC, fine, rename it V. Okay, go to the make folder, fine. So we are set with this. Okay, and now let's try to modify both the files and ready with the template. So my time varying velocity BC boundary field. Okay, so let's say time varying field supposed to be replaced with the help of this in this document. Okay, so everywhere we manage to replace it. Case of pulsatile, let inlet pulsatile BC FV patch field vector field, correct, no worry, same way in the C file also try to replace in this document. Okay, so we able to manage these modifications. Okay, so quickly let's try to compile it. So we fine, so we have a my inlet pulsatile BC. Okay, and let's also check the name is went proper. No, so we have to change this as a my inlet pulsatile BC. Okay, so that is the name I want here compared to that. Okay, so that is the change required. Now let's look at the code, what is needed. So to develop this, we required one is the mean, period, and pi is one of the scalar. That's it. So scalar is the pi, period, and mean. That is what we needed. So let's quickly add up few things from what I already have. So I already have this particular developed BC. Okay, so here we have that. So we require the mean and period as a two scalar. Okay, so let's quickly add up that scalar in the H file. We don't require any of this value. Okay, so we going to get rid of this. So mean and scalar only, that is the things, that is what we required. Okay, so I suggest you try to develop this entire BC in the similar spirit what we already did for all different boundary conditions. Okay, but I am quickly adapting few things. Okay, so that is what we have now. Okay, so along with that, so we require the u mean and the period. That is the two things we required. So quickly also here we try to change the same way C and .h file. Okay, so in the C file we require this period. Okay, so that is what we needed. So we change this as a period. Same way all the constructors you have to change it. Second one, then here as well. Okay, and it's supposed to be empty. Okay, so don't forget, otherwise it give you the error. Okay, so here it is supposed to be the empty. Okay, and then last line here. Okay, so we are set with the all the constructor. Okay, along with the constructor, what is needed, we require this few scalar, phi, pi, and all these values. That's it. So update in case of this. Fine. Okay, so let's say we require the mean. So you activate the mean. Period we required, we activate the period. Okay, so mean and period we define. Pi as a scalar we define. We require the current time, so we say current time equal to the pointers we use and set a current time, and this is exactly all this terms that is needed to generate this waveform. Okay, so that is what we required, so we adapted that. Okay, one thing we adapted in this, we try to look at the surface normal. Okay, based on the, because in the engineering domain we have a proper aligned inlet or outlet, but when we go with the biomedical domain, it's not necessary that the patch is aligned with any of the coordinate system. So at that time, if we require the normal to that particular patch, we can add up the temp vector field n is patch.nf. It gives you the normal to that particular patch. Okay, so it will quickly give us the normal to that particular patch, and based on the normal we can apply the velocity conditions. Okay, so that is what needed, so that is we adapted from here. Same way for writing purpose we require this 2 line only, so let's change that 2 line as well. So we require this 2 line here. Okay, so we are set with this pulsatile class of BC. Okay, so let me clean it and compile it again. Okay, so we are set with my inlet pulsatile BC. So it is very simple class of boundary conditions, okay, where we have to go with the biomedical class of the data, and we have this very nice waveform in detail, and for that entire terms is given, so straight away we able to code it. Okay, so that is the idea. So I suggest you also try to develop this, and in case of application of this, you as compared to the any arbitrary geometry, you can use, let's say, one of the flow through a pipe, but don't generate the pipe aligned with x-axis, y-axis. First generate the pipe horizontal, then incline to some 30 degree or so, so your patch is not aligned with any of the coordinate system, and in that scenario that is the perfect let's say test case to simulate this class of boundary conditions. Okay, so that is what one can do. Okay, so let's go for another class of boundary condition as well. Okay, so let's try to go towards different class of boundary conditions. So this is the last boundary condition that we're going to code for this session. It is about the polynomial patch deformation. So what is it mean by this particular thing? Let's say we have some solid object, and one of the patch is deforming with respect to time. Okay, so for that we define some way of patch deformations. Okay, so let's say think about, let's say cavity. Okay, flow inside a cavity, and let's say bottom of the cavity is deforming based on certain polynomial laws. Okay, so that is what it's mean. So if that is the case, we define, let's say, z is the, let's say, how it is going to deform, and it going to describe based on the two direction x and y. Okay, a new coordinate system is set up that will be used for the polynomial. So x-axis, y-axis denote the transformation from the fixed coordinate system, origin denote the origin of the new coordinate system, diff time control how long time the deformation should be take place. Okay, so how much time the oscillation or deformation you want to continue for, let's say, cavity flow or any other class of the tutorial. Okay, periodic, if set to 1, if the deformation should be moved back to the original position after the deformation, and then repeat. Active flow control type of the things. So that is what needed. So for that, first the point on the patch related to the coordinate system of the polynomial are found. Okay, so how many points are available on that particular patch, we identified that. Then these points are then rotated from the fixed coordinate system into the coordinate system for the polynomial point of view. Okay, then rotation is done using the Eulerian angles. So Eulerian angle calculation we're going to use and rotate that particular point, where line of the node n is the intersection between the two coordinate system xy and in the xy planes. Okay, so that is how we can identify the line of the nodes. Okay, alpha is the angle between the x-axis and the line of node, b is the angle between the z-axis and the old z-axis and the new z-axis, and gamma is the angle between the line of node and the x-axis. Okay, so that is how we can define the x, alpha, beta and gamma. Okay, and this is the rotation matrix. So r, if you know, so based on the r we can calculate the p, and p is the nothing but the points for which we are modifying the system. Okay, so for that I already okay, first of all, this particular polynomial patch deform BC I adapted from the open literature, you can say. Okay, and I like that particular BC because it is little bit complex in nature and it requires so many terms to incorporate and all these things. Okay, so I will quickly show you entire of the coding, and let's go through that part. Okay, so let's say this is what we have, the final one, my polynomial velocity. Okay, and let's first look at, so I'm not going to develop this, but I will go very quickly walk through it. Okay, so that is the idea behind that. So few of the let's say member or the variables required. So based on this particular functions, okay, x2, x1, y2, y1, okay, all these things, we require certain constant, x-axis, y-axis, period, and how much deformation time we require, origin, and the point vector field p0. That is what we are declaring here inside the private part. Okay, so it is belong to this particular class only. Okay, so it is belong to the my polynom velocity point patch vector field. Okay, so it's belong to that only, and few constructor. Okay, here I'm not using any value, okay, or I am not adapting any value. Okay, so I'm not defining any new member functions. Okay, so quickly we can assign the value the way we are doing. Okay, we can read that values. Okay, scalars, fine. Then all this the same way we are defining everything in for other boundary. Okay, this is actually the source code. Okay, so we go with the point patch. So whatever the patch on which we apply the boundary condition, we find out the point for that patch. Okay, and from that particular patch we define the origins, and we are reading that origin. So based on that origin, we try to look at the, let's say, relative point p0. Okay, and that is what we're going to adapt from there. Okay, and this p0 is also we are reading. Okay, so that is we adapted, and then we have a x-axis, so the z-axis, then x original axis, xyz axis is the original axis. Okay, now we for the Euler angle calculation, we are constructing the n line alpha, beta, gamma, and this is all the root of this particular 1, 2, 3 up to all the 9 term. Okay, that is what we needed, and then from that we construct the tensor as a R rotational matrix, or the tensor we constructed, inverse of the tensor, then p vector we define, and then we say vector field is sd equal to p rho, and for all the points, okay, we try to look at this p. This is what this particular equation we are coding here. Okay, in this particular line. So that is the same equations we want to look at in, let's say, z direction. So we try to define all this polynomial coefficients. Okay, and constant is 0, so this goes there. Okay, so that is very quickly one can define that, and then rotate back to the original. Okay, so I understand it is not the straightforward way to look at the BC, but why I adapted this, to give you the idea how one can construct very complex BC as well. Okay, so that is if you know the proper understanding about all the variables and everything, then it is very easy to code it and then construct the BC. Okay, so that is what the plan to showing this one class of the BC. Okay, and then finally we can say if period is over or period equal to 1 or not, depending on that it will continue to modify it. Okay, so that is the idea. Okay, and then we say with the help of vector operator sd multiply define time period. So based on that it try to oscillate that particular patch. Okay, so that is the idea behind that. So with this we will stop discussion about the boundary condition creation. So in this particular case we try to develop couple of boundary conditions. Okay, and couple of we quickly walk through it. Okay, so I suggest that you also try to adapt few of the, let's say, research paper and identify the proper boundary conditions and start developing that boundary condition test case, and apply your developed boundary condition on your proper test case and have an idea how one can quickly simulate it, develop it, and then go ahead and finish the task. Okay, so that is all about this boundary condition creation.